ID the Future, a podcast about evolution and intelligent design.
Welcome to ID the Future. Today, host Eric Anderson begins a two-part conversation with Dr. Bijan Nemati about the search for habitable planets. Whether you believe there's intelligent life elsewhere in the universe or not, Dr. Nemati says we can all be excited about the quest to answer this age-old question. In this first half of the conversation, Nemati provides an overview of exoplanet discoveries of the last 25 years, including how the technology for finding exoplanets has advanced. Nemati brings us right up to the present day, including the James Webb Space Telescope launched a few years ago. He also discusses his work on the soon-to-be-launched Roman Space Telescope, currently being tested and calibrated for a new deep space mission. Now, at times, Dr. Nemati shares some of the technical aspects of the search for habitable planets. But hang in there. This is an update about an exciting area of space exploration you don't want to miss. Here's Eric now to introduce his guest.
Are we alone in the universe? This ageless question has been pondered by philosophers since the beginning of humanity and has provided endless fodder for science fiction authors and Hollywood screenwriters. However, with recent technological advances, in just the past couple of decades, this question has become one of the hottest research topics in science, spawning several NASA missions and an entire discipline of astrobiology. Hello, I'm Eric Anderson, and on today's ID the Future, I'm honored to be joined by Dr. Bijan Nemati to discuss current and upcoming efforts to search for other habitable worlds. Dr. Nemati received his PhD in high-energy physics from the University of Washington and did postdoc work at the Cornell Synchrotron. He later worked on advanced astronomical instruments at the Jet Propulsion Laboratory and on NASA's Space Interferometry mission. Welcome, Bijan.
Hi, good to be with you, Eric.
So I had a question for you before we jump in. I know you were at the University of Washington. Was that related to some of the quark decay detection work that was done at Stanford Linear Accelerator?
Yeah, at that time, the Stanford Linear Accelerator was still active as a high-energy physics lab. And the original experiment that had discovered the charm quark and actually thereby verified the validity of the quark theory was only just recently completed. And I was working on the third generation of that experiment.
Okay.
An experiment called Mark III. Yeah.
Yeah, I ask because I'm embarrassed to say I live a couple miles south of the Linear Accelerator, and I've never been up there to visit. I'll have to go take a tour.
I used to be a tour guide there, I could have given you a tour.
There you go.
25 years ago.
Yeah, exactly. Well, I'm absolutely honored to have you on this show today. I know you wouldn't say this for yourself, so I'm going to say it to let our listeners know that in addition to being involved with intelligent design and a friend and collaborator with so many well-known ID colleagues, Bijan is one of the world's leading experts in the field of exoplanet discovery, particularly as it relates to coronagraph imaging and spectroscopy. So I'm kind of like a kid in a candy store today because I've followed the exoplanet hunt basically from the beginning and used to go on the website every day and see how many new candidates had been proposed and how many had been confirmed, and followed the NASA missions, but from an amateur perspective, of course. So I'm really excited to have you as an expert in this field to be with us today.
Thanks. Happy to be talking about it.
And by the way, did you happen to take in the recent total solar eclipse?
Yes, I actually went to Dallas for it. And between intermittent clouds, just at the right moment, I happened to be standing in a place where I saw it.
Oh,
and it was
sweet.
Wonderful.
Oh, that's great. Yeah, that's awesome. I'm glad you. What was the prior one? Was it 2007? Or sorry, 17?
17? Yeah. I barely made that one. I didn't make it to a good location, but I know that my friend Guillermo Gonzalez, he was not many miles from where I was this time, and I think he took some interesting data. I'm excited for him to actually publish it.
Yeah. Of course, he and Jay Richards talked a lot about eclipses in their wonderful book and documentary, The Privileged Planet. So that's great. Yeah, I had a real nice view for 2017 eclipse, and this time we got to experience a little bit of it, but got clouded out there right at the moment of totality. So it was fun to see everything go dark and the birds go quiet and everything, but didn't quite get to see the corona or anything like that this time around.
Yeah. It's a
So,
gamble.
yeah, exactly. That's what I kept reminding the family. It's a 50-50. We may have clouds or not, so don't feel bad. So, hey, Bijan, we spoke several months ago about the work you're currently doing on the chronograph imaging for the Nancy Grace Roman Space Telescope. Just remind us a little bit what you're working on there and when that's anticipated for launch.
Yeah, so the Nancy Grace Roman Space Telescope, or just Roman, is a Hubble-sized telescope that is slated for launch in about a couple of years. I don't exactly have the launch date in my head, and I think it's, it kind of slips a little bit, so it's not even necessary to try too hard to remember it. But basically, this was a telescope that was donated from another government agency to NASA, and NASA didn't quite, for about a year or two, didn't know quite what to do with this thing. But eventually, they decided to turn this into a dark energy telescope, dark energy research telescope. So the way these space telescopes work is the telescope itself is essentially, you think of it as a facility. It grabs a bunch of light and it compresses it to a compressed beam. And then it can distribute it or send it to one or another instrument that's attached to it.
Mm-hmm.
And so the bottom part of the telescope is just a bunch of instruments. The Roman telescope originally had one instrument. It was a instrument geared towards measurements that would help address some questions in the research in dark energy. And it was proposed that they could also add a second instrument that would be a first high-performance space coronagraph for direct detection of light from exoplanets and the characterization of that light. And so that was when I joined this effort in 2014, originally as the detector lead. So I was the one who would decide or make the case to NASA as to what type of detector they should use. And we picked that. And then after that, I got a different role. I was the integrated modeling lead, which is where you model everything, from the mechanical disturbances to thermal and heat, inflow. And then how is this thing going to slightly distort, and what would that do to its ability to cancel the star's light, which is, what coronagraphs do. And I can tell you more about that if you want.
Yeah. So you've been at this a decade, it sounds like, for this particular mission.
Yeah, it's been a while. Yeah.
Yeah. And for those who may not know, go ahead and tell us a little bit about a coronagraph. What do you mean by that?
Bernard Liot was a French astronomer in the 30s, and he wanted to, in fact, it's funny, we talked about eclipses. He wanted to create artificial eclipses just on his instrument any day of the week. And so he created a device, an optical contraption that would allow him to blot out the sun's photosphere so that he could see the corona. And so to measure the corona of the sun, and so he called it a coronagraph. A variation of that was proposed to be used sometime recently, much later than Bernard Liot's time, that would allow you to aim a telescope at a star and blank out the star and see the region around the star to look for dim companions. That's the way astronomers would for something that might be nearer the star, including its planets. It could have a planet. Now, to give you an idea how hard a job this is, if somebody was to look at our solar system from, let's say, 10 parsecs away, that's like 30 light years away, they would see our star, which would be a nice little star. And then if they had a coronagraph, well, let me not go to the coronagraph. Let me just say that if they could see our star and Jupiter at the same time, they would see something that's 1 billion times less bright. Now, almost no detector can see two things that are that bright at the same time. You can play tricks and make that happen. But that's not actually the real problem. The real problem is the wave nature of light. It is God-given. Light is a wave, and therefore there is no escaping it. That because it's a wave, it is going to diffract. And diffract means it will turn into a blob in your telescope. Now, the blob can be very sharp and narrow, but it's still a blob. And the bigger your telescope is, the sharper and smaller the blob is. So it's reciprocal. So your small telescope will make big blobs of every star in the sky, and your big telescope makes small blobs. Nevertheless, for any reasonable sized telescope, the blob is big enough to obliterate the signal from Jupiter. So if you're looking at our sun, you would see the sun, and then you would see under its wings, as it were, Jupiter's light basically at a level of about 1 billion times lower. Now, for an Earth, it's about 100 times worse than that, or at least 10 times worse than that. So we're talking about, suppressing the light by a factor of 10 billion for an Earth. And that's a very mighty task. To do that, you would have to actually manipulate the wavefront that is coming from the distant star and the distant planet. And by that manipulation, create a dark zone around the star such that the planet could be seen.
Yeah.
And it's a very advanced art of using deformable mirrors and active optics. And it's very high tech that basically no NASA mission up to now has been using the kind of technology that Roman will be equipped with its coronagraph, these high density deformable mirrors and other active optics.
So that's what you're working on, is this new best-in-class, first-in-class coronagraph for Roman. And just a question for you, when you say that Earth is another 10x or 100x, but let's call it 10x harder than Jupiter, is that because of distance, size, or both?
Both.
Okay.
It's closer and smaller, both of which affect its relative size. I made it sound very hard, and it's terribly hard, but it's not quite as hard as my numbers.
Okay.
The peak of the star compared to the peak of the planet is the kinds of numbers I mentioned.
Yeah.
But the planet isn't under the peak of the star. It's in the wing of the point spread function, to use a fancy jargon of the optics people.
Yeah.
And there, it's a mere 40 million times.
Oh, there you go.
Yeah, much easier.
And
so you're taking a needle out of a haystack that's 40 million times taller than the needle or something.
Right.
It's very tough job.
And this coronagraph that you're working on is a precursor to the Habitable Worlds Observatory, or is it confirmed yet that it's going to use a coronagraph rather than a starshade, or what's?
Well, it's a very good question, actually, Eric. The Decadal Committee on Astronomy and Astrophysics that just finished its previous decade's work in 2021, because of COVID, the report came out a year late. They recommended a telescope, a space telescope, that would form as an observatory, that'd be the platform that could enable the detection and characterization of Earth-sized planets around the habitable zones of nearby sun-like stars. And so they called for, they suggested something like a 6-meter diameter telescope. Now, to give you an idea, Hubble is a 2.4 meter. Roman is a 2.4 meter telescope. That's the diameter of the primary mirror. James Webb, that just went up successfully, is a 6-meter telescope. So they figured, well, we desperately need bigger diameters, and we know we can do a 6-meter at least. We've done it now once. And it's because basically it's very difficult to fold up a mirror to fit in a fairing of a launch vehicle, and then unfold it and have it phase up properly, which means it looked like a part of one mirror. At any rate, they suggested a 6-meter telescope, and based on some calculations that was offered to them, they said, well, optimistically, if you look at 100 sun-like-ish stars, you might see a couple of dozen Earth-type planets. But they were very generous about what they called Earth-type.
Yeah.
And, around ID circles, we were a little more meticulous or more exacting about these things. Yeah. So from that committee's point of view, they said, well, just let's focus on the radius of the planet. Well, the type of the planet, a terrestrial, rocky planet. Then the radius from the star would be kind of a Earth-Sun kind of distance, and the type of the star. The star would be a sun-like star. Although they were there too, they were a little generous. Our star is a G star, and the bluer star than us would be like an F, and a redder would be K. So I think the FGK. Look at the nearest 100 FGKs, and then look for how many Earth-sized planets you'd see at about the habitable zone of those stars. And of course, the habitable zone The traditional meaning of the habitable zone is very simple. It's the radius around a star at which you could have liquid water somewhere on a planet.
At the
Now,
surface, yeah.
Yeah, but there are all kinds of more refined habitable zone definitions, and it is useful to have the original vanilla one, and then to have
Sure.
the other ones added on with exact stipulation of
Yeah,
what you're
so let
talking
me
about.
jump in a second because you mentioned a lot of stuff very quickly
Sure,
here.
sure.
So, just for, I think a lot of people know this, but for listeners who may not, when you're talking about going from a 2-meter telescope to a 6-meter telescope, that does not mean that you have 3 times the area, right? Because you're dealing with, what is it, pi r squared? Or
Yeah, exactly.
so it's
You get
much,
r
much
squared,
bigger.
so it's like 9 times the area, the collecting. So as a light bucket, as we call it, it's 9 times more effective. But
Hmm.
its real advantage is coming from the bigger diameter makes that blob thing I was talking about smaller, so that the that blob's official name is the point spread function, or PSF, point spread
Okay.
function. A point should look like a point, but because of diffraction, it's spread. And so
Hmm.
that point spread function gets narrower and narrower, becomes a smaller and smaller disk on the sky, the
Yeah.
bigger your telescope is.
So, in layman's terms, you could think of it as a sharper image, right? I mean,
Exactly. If you had a
yeah.
binary star, if your telescope's not big enough, you just see one blob.
Hmm.
As your telescope gets bigger, as long as the quality's good, it starts resolving them into two, and you see, that's a binary star.
Right, right. Okay. And then, yeah, I remember one of the announcements that came out about the first Earth-like planet that had been discovered, exoplanet. But when you delved into the press release a little bit, the only characteristic I think in that particular press release was size that they were focusing on.
Yeah,
There's tons of other things that, like you say, in the ID community, we focus on in terms of having an Earth-like planet. But you got to start somewhere.
that
So,
starts
so
somewhere.
yeah,
Yeah,
you look at you as you said, the sequence of stars. You look at the right distance from the stars to have, let's say, liquid water at the surface, and then you're looking at Earth size, and you kind of come up with a group to say, okay, we're going to look at these planets and see what we can figure out. And so that's the next mission, right? Or is Roman also going to be looking specifically for that?
you remember at the beginning I mentioned that Roman was a gift telescope,
Mm-hmm.
and you don't look at a gift telescope in the pupil.
In the mouth, right? You're right. There you go. In the pupil. There you
I
go.
just coined a new proverb.
Yeah,
Uh,
yeah. Trademark that right away.
Yeah, yeah. It turns out, the business of making coronagraphs to do these factor of 40 million type suppression, or factor of million type suppression, is the business of, it is very mathematical project, because you're essentially doing this really crazy stuff of measuring the electromagnetic field at the focal plane of your camera, at the focal plane of your telescope where your camera is, and then from that field morphology that you're measuring, you go, what would I do? How do I poke at this upstream of where I am, where my deformable mirror is? How do I deform it so that I null out this light and I don't see any from the star?
Mm-hmm.
And you do this iteration after iteration, hour after hour, and eventually this gets darker and darker in the zone where you would want to see a planet. Then when you get the really dark zone on your test star, you aim your telescope at the one where you want to see the planet. Or you do that on the same star. But at that point, you then have a chance to see the planet.
We've hit a bunch of really technical stuff here in the first few minutes, but let's step back just for a second. What are we talking about when we talk about the search for exoplanets? Why are we doing this? What's the interest in this effort?
Yeah. So there is, at multiple levels, we can say there could be very, legitimate great interest. Of course, the whole enterprise of science is the enterprise of finding out what is true in the world. I mean, that's like the grandest definition of science. And in astronomy and astrophysics, you want to know, what are the questions, like what are the processes that form planets? What are the processes that form stars? What is the likelihood that a planet would form the way the Earth has, with such perfection in so many of its qualities? And in fact, the solar system that
Mm-hmm.
has so much perfection in its qualities, and one could go into that. Those things are all legitimate studies. Now, of course, philosophically, we can start diverging there. If we think that the Earth is something, if we come to it with the presupposition that the Earth is actually common, because we cannot possibly be rare, because otherwise that would beg the question of where did we come from? Are we designed? Are we not designed? Is it just law or chance that could generate our existence? Then you're kind of inclined to want to show or want to see that everywhere you look, you see evidence of Earth-like planets and with evidence of life, if you can measure it. And so you are, in that sense, quote, optimistic, But on the other hand, to somebody like me who appreciates a designed world by a creator, I have no problem doing the investigation and finding out what is the answer. Did God make another planet like ours, or did he not? And so that is sort of a very legitimate question. And it's one that one would, just want to address with a mission like this. And I think you can be on either side of this question and totally be excited about making this work.
Yeah.
I would say, though, having said that of course, one thing that is really important, and again, that applies to both sides of the philosophical sides of this, is that if you're designing an experiment of any kind, whether it's a telescope to see things in space or, some tabletop laboratory experiment to measure some physical phenomenon, you want to make the most sensitive instrument you can. Why? Because the question you're answering, let's say that you made a telescope that just is so poorly made, it's not sensitive to the existence of your signal, or your planet. And you say, and gee, I didn't see anything. And everybody else will say, well, of course you didn't, because your telescope is not good. And so for both the optimist and the, I don't want to be called pessimist. So I would say the one who is, more open to all possibilities. I would say we both really want the most sensitive instrument that we can build, because we would like these questions to be adjudicated by observation.
Yeah. Well said. And we should point out that in terms of intelligent design, there's no problem with the idea that there might be another Earth-like planet, and not just Earth-sized, but Earth-like in wonderful parameters.
Absolutely.
That's not against the ID approach at all. The question would be then, moving on from that discovery, how did it get there? What are the parameters? How did it form? Those kinds of things that we look at when we look at Earth as well.
Exactly.
So take me through just historically, and I know you could give us a whole semester course on this, but maybe briefly, I'll just mention a few missions, and maybe you can give us a couple of sentences about how these missions led up to where we're at today. So initially we had a bunch of, so the first exoplanet discovery, depending on which one you count, somewhere around 92 or 95. But the key telescopes were largely Earth-based.
That's right.
And we were using those with some interferometry, right, to try to make that sharper image than we could get on Earth.
Those were spectroscopy. When we learned how to do very, very, very precise spectroscopy.
Okay.
Then we were able to see the Doppler shift of the star and inferred indirectly that there's a planet.
Okay, so most of those were Doppler shift discoveries. Yes. And then what about transit?
Transit came along in the early 2000s, particularly with the Kepler mission that just exploded into the scene with an incredibly successful
So Kepler, now we've moved off Earth. We're now in a space-based observatory.
Yeah,
Kepler,
that's right. That's right. We were in space-based. Now, the ground-based, because of the wild success of those original experiments, those techniques have been perfected and improved. And radial velocity, that technique, which is this ground-based spectroscopy looking for Doppler shifts, has been tremendously successful, and it's not stopping. It's just moving and, doing its thing. But that one is more sensitive to heavier planets, because the lighter planets are not going to push and pull on the star to cause much of a redshift signal.
Yeah, and give us a visual image there. So when I think of this particular technique, for maybe listeners who aren't aware, you're talking about, imagine you're out in the backyard with your small child who's 5 or 6 years old, and they say, swing me around. You grab them by the arms, you swing them around. They're going around, but you're also shifting subtly back and forth as you do that, right?
That's right. You said it better than I would. I'm glad you attempted that. Yes, I can say it a little more bookish, like action and reaction. There is for every action, there's a reaction on the other object. So as the planet is drawn to the star is actually drawn to the planet, but by a proportionately smaller
Sure.
amount. And that small amount is like tens of meters per second. It's almost like the speed of a car. Well, the red shift or blue shift from a car, the light of a car coming towards you or away from you, is just infinitesimal. It's very, very hard to measure that. And there's
Mhm.
all kinds of atmospheric effects when you're looking at the star through our own atmosphere that are going to cause those shifts. So you have to kind of be able to subtract those effects out, and they're variable in time. And so
Mhm.
it's a mighty feat to be able to do these measurements.
Okay. But this wobble approach, I'll call it, which is sort of the layman's term there, or the radial shift, is them seeing the star shift slightly back and forth as that planet is orbiting around it, right? And
That is
and you
right.
mentioned a larger planet. So if I were trying to swing, a teenager around instead of a small child, I would be wobbling back and forth more because there's more gravitational influence from that other object, right?
That is right. And so that is why these radial velocity, or RV, we call it, measurements, are limited somewhat to the
Yeah. Okay.
heavier.
But there've been, and I don't remember the numbers, but there've been what, a couple thousand of those at least identified
Many
that way.
hundreds. It's probably, I'm not fully up to date, but I would say the ones from RV are probably on the order of 1,000.
Okay.
And then there is maybe twice as many transits.
And tell us about those. That's a little simpler to describe, but
Yeah, transits are more fun to describe in that if you're looking at a star, now imagine that star has a planet. That planet is orbiting around the star. Now, that planet could be orbiting in a way where you see the full circle of the orbit of the planet as a circle on the sky, imagine.
mhm.
Well, there is no transit in that case because the planet is never in front of the star. But now, if you imagine the orbit of the planet is such that you don't see the circle, you see almost like a line. The
Yeah.
planet's kind of going around the star, and your eye is in the same plane as the orbital plane of the planet. Well, now what you're going to see is the light from the star is going to get dimmer. How much dimmer? By about 10 to the minus 4, 1 part in 10,000. So if you want to measure this effect, you have to be able to measure the drop in the intensity of the star's light by a part in 10,000. But not just that, you have to measure it better than that so that you can be sure you saw something.
hmm
And so it's part in maybe 10,000, 100,000, and then at that point, you really have quite the sensitivity to do it. Kepler very, very ingeniously, in a sense, it was ingeniously simple idea, very brilliantly conceived and executed, and yeah, thousands of transiting planets.
And those you also have to watch for. Well, it depends on how quickly the orbit is, right? But if you're looking for
Exactly.
something a little bit farther out, you got to watch it for several years to see it come through 2 or 3 times, so you're sure you got the right measurement, right?
Yeah, yeah. If we were going to try to look for an Earth like somebody else, our orbit is a year,
Yeah,
and so
right,
you'd have to wait a few years. And Kepler was only supposed to be up there for 5 years. I mean, that's like how much
right.
lifetime these telescopes have, and there's only so much you can do.
Yeah, but it got extended a few years, right? I think it ended up
Yeah, yeah, it
around
did.
8 or 9 years,
Yeah.
and then
hmm
okay. So Kepler was Kepler primarily transit based
hmm
then in terms.
That was
Okay,
all it was. Yeah,
okay,
it
and it
just
and it
looked at one part of the sky and
okay,
just stared there forever.
okay.
And yeah,
Yeah, and some of that data I think is still being analyzed, right? So there may be a few more, but I was reading
yeah.
that about more than 2,500, close to 2,600 so far have been confirmed. So that's pretty
hmm
impressive.
hmm Yeah, it is quite
Okay,
impressive.
and then real quickly, what was the next one? Chandra X-ray Observatory.
Yeah, that is an X-ray observatory. I am not aware of a major, contribution from Chandra in the exoplanet area. If there is, I don't know any of it because in the X-ray, it's difficult for me to see how you would see a signal of any kind.
Yeah. I think I had read about one proposed candidate from Chandra, but yeah, it's definitely not focused on that mission would definitely not focus on exoplanet search, right? Okay,
Right.
then we had Spitzer, which had a few, again, that was mostly looking at star formation, I think, but there were a few
Yes.
exoplanet discoveries that came out of that.
Right.
And
Right.
then what was next? TESS, which was really more focused on
That's
exoplanets, right?
exactly. TESS is still in operation. Yeah. So it is doing transits, by, very large numbers.
Mm-hmm.
And the spectroscopy is also one of the things that TESS is supposed to,
Okay.
excel at. It does. And to understand the spectroscopy, imagine you now have the light from the star before the planet has transited in front of it. So
Mm-hmm.
you measure a faint amount of light because it's from another star, and now you let's pretend you use a prism. You turn it into a spectrum. You measure that spectrum. Now, when the planet goes in front of the star, what's going to happen? Well, the amount of light is going to go down, of course, but there's a subtle other thing that happens, and that is that the planet has a teeny weeny atmosphere around it. And there is a spectrum to that atmosphere. In other words, the light from the star that goes through the planet atmosphere is going to be there are going to be some absorptions of that
Right.
starlight by the planet's atmosphere. But you can imagine what a tiny effect that is, just staggeringly tiny effect, because the planet is tiny. You're already, the whole effect is like 1/10,000th of the starlight, is dim. And now you're trying to subtract the spectrum of the starlight with the planet in front of it from the spectrum of the starlight without the planet in front of it. And for those who are familiar with math and statistics more, you know that when you subtract two noisy numbers that are kind of similar to each other and are large numbers, you're going to get a huge amount of error noise. But it is worth doing, and there's some amazing spectra that people scientists have been able to obtain from this technique. But it's the subtraction that puts a lot of noise into the measurement. But it's possible. It's really cool that people can do that.
Okay, so TESS is, if I'm understanding you right, TESS is combining both the transit method with visible light and spectroscopy method that
That's
you just
right.
talked about? Okay.
Yeah.
All right. And then the most recent telescope that everybody's excited about, James Webb, which again is not focused on exoplanet search, but last January they did announce that they had discovered one exoplanet with James Webb. And that's primarily an infrared telescope, right?
That is very much an infrared telescope. That is right.
Okay.
And it's a wonderful telescope, very capable, but it's going to be, it's going to have some techniques available to it for exoplanet detection, but primarily, transit is going to be relatively easy for James Webb.
Oh, okay.
But the reason James Webb by itself is not, going to be the way to the next stage and habitable worlds is needed is that James Webb doesn't have the instrumentation, the deformable mirrors and active optics to manipulate the starlight so that you can cancel out the starlight. And so you're always going to be stuck with a lot of, just an insurmountable, unless you're looking at a transit, but you can't do a direct detection.
Okay.
Where all the light you see, approximately speaking, is the planet light.
Okay. And so that now brings us to, and we already talked about this a little bit, but that brings us to the Roman Space Telescope, which is going to use visible light, right, with your coronagraph that you're working on, you and your team, and others are working on that. And that is going to allow for direct optical detection of planets, right? That's the idea?
That is right. Direct optical detection of planets, relatively big ones. We don't think we can exactly get down to a Jupiter, but the very, very largest gas giants, maybe if everything goes super, super well, we might have a shot at it. But this was never meant. Its budget was constrained and its mission was constrained. It was supposed to be a technology demo for the next space telescope.
Okay, perfect. So tell us about the next one.
Yeah, and then before I do, Eric, I do have to kind of do a shout out for Roman in that just as we speak, almost like today, it's being shipped
Wow.
from Jet Propulsion Lab to where it's going to get mated with the telescope. It's going to be tested over there, and then it will be assembled. And the next 2 years, it's going to be basically in the process of getting assembled into the telescope. But we just finished thermal vacuum testing of this thing and verified that everything is working great.
Oh, fantastic.
So we're very excited.
That's great news. That's great.
So I forgot your question now. Sorry.
Yeah, no. That's awesome. And I'm sure, did you guys get to go out for pizza after or something?
Yeah, except I'm not in California. I just heard that everybody else was celebrating and taking pictures in front of the truck.
Oh, that's great. That's great. Well, congratulations that's a huge achievement. I know, like you said, you've been working on this for 10 years, so that's a big deal.
Yeah.
Fantastic.
That was Eric Anderson speaking with Dr. Bijan Nemati about the search for habitable planets. Look for the second half of this conversation, where Dr. Nemati will go into more detail about the next space telescope to be launched sometime within the next 2 years, the Roman telescope. He'll also share some intriguing details about another future probe currently in the works called the Habitable Worlds Observatory. So don't miss part 2 of this discussion. For ID the Future, I'm Andrew McDermott. Thanks for listening.
Visit us at idthefuture.com and intelligentdesign.org. This program is copyright Discovery Institute and recorded by its Center for Science and Culture.